All right, let's talk osmolarity and tonicity. All right, so first of all, what is osmolarity and what is tonicity? So the easiest way to explain it is that they're both snapshots in time. So osmolarity is going to be sort of your solution before equilibrium, and then tonicity is going to be your solution after equilibrium has occurred. So if you sort of look at a cell, and you sort of see before and after what's happening depending on whatever solutes you're given, if they're permeable or not permeable, and then after equilibrium, what you see, that's sort of going to tell you the difference between osmolarity and tonicity, and we'll get more into that and we'll explain it. So both osmolarity and tonicity, however, they're both referring to the solution. Not the cell itself, but the solution. So basically, it's saying that what is the solution in relation to the cell. So to explain that, let's draw a cell. And we know that the inside of our cell is usually around 300 milliosmoles, right? So if you have and that's 300, not 3,000. If you have a solution that's isotonic to the cell, that means the solution is also going to be 300 milliosmoles. If you have a solution that's hypertonic to the cell, that means it's going to be something greater than the 300 milliosmoles inside the cell. And then if you have a solution that's hypotonic, that means that it's going to be something less than the 300 milliosmoles inside of the cell. So if you can keep that in mind, whether it's osmolarity or tonicity, anything that you're talking about, the outside of the cell, the value that's on the outside of the cell in the extracellular fluid is what's going to give you your designation of whether it's hypo or hyper or iso. The inside of the cell is not going to dictate that. It's going to definitely influence it, because if the outside is, depending on what the outside is in comparison to the inside, but ultimately whenever you're answering the answer choices, it's going to be dependent on the ECF values, not your ICF values. So anyways, let's go ahead and talk about a couple parameters before you start all the questions and everything. So some substances, as you know, will definitely cross the cell membrane and they'll equilibrate, right? And then you have other substances that won't do that at all, so they're impermeable. So some general examples that they gave for permeable versus impermeable is like sodium and chloride. That's generally going to be impermeable, so it won't cross the membrane. Right? But then something like urea or glycerol, that might be permeable, so it might be able to cross the membrane and equilibrate. However, regardless of any of that, if you're given a reflection or a permeability coefficient for a certain solute, on the exam, if you're given one of those, use that. Don't use your general knowledge. Use the actual coefficient that they give you. So for example, if they give you a reflection coefficient of 1, right? Even if they give it to you for something like urea, which you know is permeable, even if they give you a reflection coefficient of 1 for any solute and they list it as that, it will not pass, because basically what it's saying is that solute will be 100% reflected. On the other hand, if they give you a permeability coefficient, once again, it could be for anything. They could give you a permeability coefficient for sodium and say it's 100%. If they give you a permeability coefficient for a solute, and they say it's equal to 1, that means that the solute is 100% permeable. Right? So what does that mean for the other, if these values were 0, right? So basically here, if the reflection coefficient is 1, that means it's 100% reflected, which means it's definitely not coming in, it's just being rejected. It's trying to come in, but then it's being reflected away, basically, is how you can think about it. But then if the reflection coefficient is 0, in that case, that means that the substance is 0% reflected. It's definitely going to come in. It's kind of confusing. You got to keep those two straight. And then the other one is with the permeability coefficient. If that's 0, that means that the solute will be 0% permeable to that specific membrane. So it's not going to cross through. This is regardless of what our prior knowledge is or anything like that. Whatever they give you on the exam for these values, you have to use for that. Otherwise, you'll get the questions wrong. But anyways, now that we have that done, let's go ahead and try out some practice questions and see how it goes. So the first type of practice question that they could give you is the general, just straight up cell question, which they unfortunately probably won't give you that. So but it's a good way to get down like the general concepts though. So the first thing that you want to look at is when you're looking at the cell questions are the two snapshots. So you have the before snapshot and the after snapshot. And let's say for this specific example, the inside of the cell is going to be 300, and then we're given sodium chloride, which is going to be 300, and we're given glycerol, which is going to be 50. All right. So what I mean by snapshot is basically the before picture that you're looking at is going to be your osmolarity picture, while your after is going to be your tonicity. So if you look at this right here, then the concentrations, right? So the first thing you see is that you're seeing it's going to be 350 on the outside while it's 300 on the inside. So that's going to tell you that this solution, right? Because we're talking about the solution in respect or in like relation to the inside of the cell. The solution is going to be hyper. And since we're talking about the osmolarity, the before picture, before everything equilibrates, right? Because this is equilibrium. When equilibrium occurs, we go to that side. Before everything equilibrates, it's going to be hyperosmotic. However, after is going to be a different picture because basically now what you have is you have the inside of the cell, it's still 300, but then the outside of the cell is now going to have NaCl, which is going to be 300. We're saying that the reflection coefficient for NaCl is going to be 1, meaning that it's fully reflected, and we're going to say that the permeability coefficient for glycerol is going to be 1 as well, which means it's fully permeable. Okay, so given that, I probably should have said that at the beginning, but given that, if the concentration of sodium chloride is 300 and the concentration of glycerol is 50, what you can basically do to figure out the overall concentration on this side is just to take the values of everything that's going to be fully permeable and just cross them out. If you just straight up cross them out and you just take them out of this value, then whatever's left is whatever's going to be left on the outside. So in this case, if you just take the glycerol out, it's totally gone, right? Because it diffused out, it did whatever it did, who cares? But basically it's gone, and now you're going to have 300 on this side left over from the concentration of sodium chloride. So then what this tells you is that your after picture is going to be iso. And we said there's snapshots, right? So the after snapshot is tonic. So it's going to be isotonic. So your solution started out as a hyperosmotic solution because you had 350 total milliosmoles on the outside in the ECF. Then you went through equilibrium, whatever equilibrated. In this case, it was glycerol, right? And basically you were left with 300 milliosmoles on the outside just from sodium chloride, which was left over, and that gave you an isotonic solution when you're done. So if you use it this way and you solve the equations or solve the problems this way, it'll be a lot easier, and it just saves you the hassle of sort of thinking of it in like more abstract terms. It's basically just think of it as a snapshot before, after. That's it. All right, so let's use another one really quickly, and let's just try to sort of see how many different situations you can get from this. So basically the next one, let's look at these values. Let's just make this slightly different. Let's say this is going to be now 200 over here of sodium chloride, and this glycerol value, which was 50 before, we're going to switch this up. We're going to bump it up to 150. All right, so what does that give you for your solution, right? So you take 200 plus 150 in your osmolarity before everything is equilibrated, right? And you're going to get 350 milliosmoles, which is exactly the same as we got before. It's still hyperosmotic. It's 350 milliosmoles. But whenever everything equilibrates on the other end, whenever you get the after snapshot for tonicity, what's going to happen is when the glycerol equilibrates on this side, this time around, what's going to happen is you're basically going to take out the 150 from this 350, right? And you're going to be left over with whatever was left over. Sorry, I should have done this before. On the other end, which is just your sodium chloride. So whenever you took out the 150, because it just straight up dissipated wherever it went, and you end up with whatever is just going to be impermeable on the outside, you end up with sodium chloride at 200 on the outside, which is going to give you your tonicity value. But this time around, what's happening is you went from a hyperosmotic solution to a hypotonic solution. Because the value you started out with was 350, right? Compared to the inside, compared to the 300 inside, that's higher. 350 is higher than 300. So that's going to give you a hyperosmotic solution. But then after the glycerol equilibrated out, you end up with a ECF value of 200 milliosmoles, which is lower than your ICF value of 300 inside the cell. So in this case, your solution is going to be hypotonic. And the reason why you can do this is if you have a hypertonic solution a hyperosmotic solution to begin with. As we saw, a hyperosmotic solution can lead to a isotonic solution, which was the first case that we got. It can also lead to an isotonic solution. It can also lead to a hypotonic solution, which we saw here as well. And it can also lead to a hypertonic solution as well if nothing crosses over at all. So basically, if you start off at the peak, if you start off with a hyperosmotic solution, you're going to be able to get a hypertonic, an isotonic, or a hypotonic solution from that, because basically there's no way more stuff's going to go into the outside of the cell. It's going to either leave, or nothing's going to leave, or it's going to equilibrate, and basically you can get all three of those situations. However, in the case of a hypoosmotic solution, so let's say we had a hypoosmotic solution over here. So let's say we started off with just this 200 over here with the NaCl, right? In a hypoosmotic solution, there's no way that this hypoosmotic solution is going to become hypertonic. In order for that to happen, you would have to lose, basically somehow, like this would have to come out here, or you would have to add more solutes out here. It's not going to happen, and they're not going to get that deep into it. So if you see a solution that's hypoosmotic to begin with, there's no way your answer is going to be anything other than hypotonic. Because if you think about it, the only way, basically if you think of it as like a step ladder, the only place it has to go is even lower. It can't go any higher, so it's got to go even lower. However, if you have an isoosmotic solution, that can be either an isoosmotic or a or isotonic, sorry, it could be either an isotonic solution or a hypotonic solution, depending on what the permeable solutes are. So you do sort of see the kind of like the pattern going on here. So if you start off at the top, you can go to all 3 levels. If you start off in the middle, you can go to the next 2 levels, meaning the isotonic or the hypotonic. And then if you start off as hypoosmotic to begin with, you're only going to remain as hypoosmotic, and that's it. So that's kind of a confusing concept. I don't know if that was the best explanation of that, but it's some students have a hard time with that. But if you know that, you can just basically cross off answer choices left and right, because you know that if you start off with a hypotonic or hypoosmotic, this is so confusing already. If you start off with a hypoosmotic solution, you're not going to be able to get anything other than hypotonic, basically, unless other external factors are added, but we're not there yet. You'll get there eventually. But yeah, so that's the one way that they can present this. And then there's another way they can present this, which is probably the more common or more testable way to do this, which is going to be with the ECF and ICF boxes. So basically what they're going to give you is it's the same thing. You just kind of have to think about it in the same terms, except you just kind of have to work around with what you have to work with. So let's say this is your ECF and this is your ICF, right? You've probably seen this in class. And basically what's happening here is they're giving you, instead of a before and after, they're just giving you a straight up, this is what the values are. Tell me what happens during osmolarity. Tell me what happens during tonicity, which is before and after, right? And then it'll also usually ask you for the movement of water as well. So let's say in this case you have a 300 milliosmoles of NaCl on the outside, so on the ECF side. And then on the ICF side you have 300 milliosmoles of KCl. And let's say none of this stuff is permeable at all. So it has a reflection coefficient of 1. Or it has a permeability coefficient of 0. So that's how it's going to be presented. And they'll probably give you little, like the little sigma values or whatever they are at the bottom. So watch out for that as well. So basically, if nothing is permeable here, so let's say your before, right, versus your after is what you're looking at. It's the same thing. If you want to just take away the box, it's now a cell. It's the same thing that's happening. It's just a different way to present it. They're probably not going to give you a real cell on the exam, though. That's very unlikely. So basically what you're looking at here is the before. You're just going to have 300 compared to 300. And what you're having here is you're going to have a isoosmotic solution. Right? Because the solution, which is this guy right here, the solution is going to be isoosmotic compared to the inside. And then after equilibrium, which means in this case nothing's moving, it's still going to be 300, and it's still going to be 300, which is going to give you an isotonic solution. Now, how is water going to move in this solution? It's not. Right? Water's not going to move, because basically what you're going to get is you started with an isotonic or isoosmotic solution, you ended with an isotonic solution, there's no movement. The solute concentrations are the same. Water is going to always move towards the higher solute concentration. So now let's do an example where we might get a shift in the water values. So in this case, let's say we had 100 over here for NaCl, and let's say that over here we kept it at 300, right? So right here, we had 100 to begin with. We went to 300. So in this case, what you have is a hypoosmotic solution, because the outside, the ECF, is lower, 100, than the ICF, which is 300, right? So it's going to be hypoosmotic. Nothing's moving once again. So what you're going to end up with is a hypotonic solution as well. But in this case, you are going to get a movement of water, because if you look at it, this 300 value is obviously more than the 100. Water is going to flow towards the higher concentration. So basically what you're getting in this case is that after you're done equilibrating, So that's important. After you're done equilibrating, so in the tonicity box, so like the after value, right? If you're still, if your ICF value is higher, then what you're going to have is you're going to have the movement of water inside of the cell, and your cell will swell up. And that's probably what you're going to see in your answer choices for that. So then the next thing here with that really quickly is, what if you had a, let's say the other way around. So if this was 300 and this was 100, it would go that way. Water would just flow out. So then let's say if you had a, a solution where you had 300 of NaCl here, and you had 200 urea. So now you have a molecule that's, we're going to say, is going to be fully permeable. So its reflection coefficient is going to be 0. Its permeability coefficient is going to be 1. It's going to be 100% permeable, right? So basically we're going to get a solution like that. And then let's say on this end, we're going to have 300 of NaCl, and we're going to have 50 of urea, okay? So if we do our values the same way we've been doing them the entire time, what we're going to get is the before value is going to be 500 on the outside. It's going to be 350 on the inside, and what we're going to end up with is a hyperosmotic solution. A hyperosmotic solution. But then basically what happens here is the same thing that happened on the other side. Don't get confused by like the layout of all of this. It's going to be exactly the same. So what we did on the whenever we had just the outside of the cell and the inside of the cell, anytime that you were looking at the tonicity value and there were things that were fully permeable, all we had to do was we just had to cross them out. We just had to take them straight out of the equation. So you just cross it straight out, and what you end up with on both sides, you cross it straight out on both sides. And what you end up with is 300 and 300. So you actually end up with an isotonic solution. And what about the movement of water in this case? So in this case, you're going to see no movement of water. And the reason why you're going to see no movement of water or no volume change is because this 300 and this 300, as we said, the tonicity values are what's ultimately going to determine the movement of water. So you're not looking at the osmolarity values, you're looking at the after picture. You're looking at the tonicity values to figure out what's going on there. So let's do one more really quickly to get the point across for the movement of water and make sure that we're not shaky on that at all, because it's going to come back in CPR 4 or whatever, exam 2 or whatever it is. So it comes back. It definitely comes back. So you want to get it down now. So let's say we have a ECF value of 200. And let's say we have a value of 400 for urea. And then let's say on this side, we have an ICF value of NaCl. And let's say urea is fully permeable and sodium chloride is not. So then what you're getting on this, in this situation is you're going to have 600 for the osmolarity on the ECF and 300 on the ICF. And you're going to end up with a hyperosmotic solution. But whenever you take the urea out, right, because it's fully permeable, you're going on to the tonicity, the aftershot. When you take the urea out, you end up with 200 for the ECF and 300 for the ICF, so you actually end up with a hypotonic solution. So what's the relevance of that? Why did I just do that? Because now you have to say, where's the water going to move, right? Because what's happening here was beforehand, you had 600, which was hyperosmotic on the outside, but then afterwards you had 200 on the inside, or on the outside compared to 300 on the inside, which made it hypotonic. Since the inside of the cell is more concentrated afterwards, right? So on the tonicity, the aftershot, since it's more concentrated on the inside of the cell, you're going to have water moving to the inside of the cell, and your cell is going to swell again. And basically, the main point here was that you're looking at the tonicity. You're looking at the after whenever making that designation. And it's going to be like that for every exam, like from now on, as far as this is concerned. And you're probably going to see this pop up a couple times. Like this is like, I think we saw it on like MSK. We saw it pop up a couple times on CPR. Like this won't leave. So just make sure that you get this down. If you have any questions or anything, like definitely post. But like this is definitely important. It's going to be repetitively done in future modules, so you got to know it now. But yeah, other than that, that should be it. Thanks everyone. Hopefully that was helpful. And yeah.